Adversarial examples are for neural networks what optical illusions are for humans. In 2013, researchers from Google and NYU discovered AI illusions while playing around with the new convolutional neural networks. CNNs weren't really new at the time, the first were used in the 80s and throughout the 90s. But what was new is that they finally worked. CNNs ruled all computer vision competitions and were all over the AI news. During all this hype and excitement, the researchers from Google and NYU showed how to deceive them with very simple tricks. Just slightly perturbating the input image could completely confuse the neural networks and was imperceivable to humans. Today, most people in AI don't share these strong concerns anymore, but it was a major concern at the beginning. From a safety perspective, adversarial examples are small edge cases, and they're good methods to defend against them if they're used maliciously. But left unattended, these problems can creep up on you. That's why investigating neural networks with adversarial examples should be in every ML engineer's toolbox. Many optical illusions have been so effective in understanding the human visual system that they earned the nickname the psychologist's microelectrode, a precise, non-invasive way to understand the internal workings of a black box system. Let's try it. When you move your eyes around this image, the difference in the contrast between the white and black areas and the blue and yellow areas are processed at different speeds in your peripheral vision. The high contrast between the black and white is processed quicker than the lower contrast of blue and yellow, and thus elicits a movement perception in the direction from black to blue and white to yellow. This image was created by Akiyoshi Kitaoka. It's a type of movement illusion called peripheral drift illusion. Interestingly, it also works in a grayscale version. But if you switch the blue and yellow colors, the movement illusion disappears. This is curious, but illusions are not only fun and games. They make it obvious beyond doubt that perception is doing interpretation of the world around us. This is necessary because sensory input is not always unambiguous. Illusions are a byproduct of this ambiguity resolution. The same strategy that aids perception can lead it astray in certain cases. According to this view, illusions are not bugs, but rather essential design features. If we design a robot to optimally perceive the world, we would expect it to perceive illusions. What we see and what we think we see misalign. Our vision, for example, is never free of interpretation and concepts. This is most powerfully demonstrated with bistable illusions. For example, with the spinning dancer. Some people see it spinning clockwise and some see it spinning counterclockwise. The silhouette is ambiguous, and therefore it's fair to assume both. If you get further visual clues, this ambiguity is resolved, and everyone sees her spinning in the same direction. If you keep this visual impression in your mind, you can force the visual interpretation of the dancer to spin in either direction, and you willingly switch her direction when you focus on the visual clues of the other direction. Try it. Quickly close your eyes and imagine her spinning in one direction, and the chances are high that you see her spinning in this direction as well. This is profound, because it's not like we see something and are not sure about what we see. We actually see her spinning in one direction. And we can change this perception of the same visual input just by thinking about it differently. This is what I find most fascinating with illusions. What we see, what we think, and what we hear is not the true nature of things. And even if we are aware of this, we can't unhear, unthink, or unsee them. Only our rational understanding reveals that there is indeed a mismatch. In cases where the rational argument is weak, it's hard to believe what we see. This is why some cognitive illusions are very intriguing for us, because it's hard to unthink what we believe. The same happens for artificial neural networks. They think they know what they see, but on further inspection, that's not true at all. Adversarial examples are specifically designed to deceive neural networks. But what about illusions designed for humans? Would they deceive neural networks? Interestingly enough, some researchers could show that for some illusions, this is indeed the case. The snake illusion, for example, tricked a network that was trained to predict movement in a series of given images. The special network predicted the movement of a series of stationary images. In a test case with the non-illusion images, the model did not predict any movement. Researchers also tested with other common illusions like the Miller-Lyer or the Ebbinghaus illusion. Does this mean that neural networks see the world similar to humans? Most likely not. First, there's more research needed to better understand when and how neural networks are fooled by illusions. We typically ask for introspection in humans to confirm that they see the illusion. We can't do the same thing, obviously, for neural networks. We must somehow get around this problem, for example, by looking for mistakes in a given task. And besides the problem of measuring subjective experience in neural networks, there's also the problem that neural networks are at best a crude approximation of the mechanisms in the human brain. I talked about this in one of my last videos. The problem is that neural networks rely on mechanisms that are not present in the brain, like backpropagation. And one of the biggest problems is that neural networks don't perceive images like humans do. In classical neural networks, there's no concept of peripheral vision, saccades, or fovea. But these processes are thought to be the reason for many visual illusions in humans. Whatever the reason is that neural networks appear to perceive illusions, if they don't use the same concept, there must be different causes at play. But if illusions are so important to understand human perception, how do we make use of illusions in AI? Are adversarial examples a clever shortcut or a bug in the system? To answer this question, we first want to ask a different question. Can adversarial examples that were designed for one model also fool another model? This would be interesting because this would suggest that adversarial examples are not overfitted to a specific model, but express a general property of the models or the data. This is known as transferability, and for some adversarial examples, this is indeed the case. But where does transferability come from? To better understand this, we want to first understand why adversarial examples arise in the first place. The most prevailing explanation has been that adversarial examples are just quirks of the model, and with enough training and data they will disappear. But are adversarial perturbations really meaningless? In an experiment, researchers took images from a standard Cypher-10 dataset and created adversarial examples by perturbating the images unperceivable to humans. For the neural networks, on the other hand, the images looked very different. All dogs were perceived as cats, all cats as birds, and so on. From this, they created a mislabeled dataset where all the adversarial dog examples had cat labels and all the adversarial cat examples had bird labels, and the same for all the other categories as well. They trained a new neural network on this mislabeled dataset and tested it on the original dataset. And surprisingly, the performance was not too bad. How can this happen? The network has never seen an unaltered version of a dog, only cats labeled as dogs. The misconception is that we humans think that these perturbations are meaningless, but for the network they are highly predictive and generalize well. The very act of extracting adversarial examples is finding these relevant patterns in the network. This would be the same as asking a human how they detect a cat, like pointy ears, the shape of the nose, and take this and disguise a dog as a cat. Even if you've never seen a real cat before, only dogs disguised as cats, you might be able to detect one if you come across one. Because we require the perturbations to be meaningless, this filters out all the robust features that humans rely on, and only leaves the non-robust features that humans find meaningless. The fact that a neural network trained on this mislabeled dataset also generalized to the original test set indicates that non-robust features exist and that they are sufficient for good generalization. For a deep neural network, there's really no reason to prefer robust features over non-robust features. After all, this concept is human-made. Interestingly, they also showed in a second experiment that when they create a dataset with only robust features and trained a normal neural network on it, it was also robust against adversarial attacks. This indicates that adversarial examples are not quirks of the model, but properties of the data. This also explains why some of them can be transferred. So are adversarial examples a bug or a feature? Both to a certain extent. In humans and other animals, evolutionary pressure created a system that is able to perceive and reason about the world in an effective way. And because of the ambiguity of the sensory input, there can never be an exact solution. Sam Gershman argues that an optimally designed system is expected to take shortcuts and should perceive illusions. The fact that neural networks are susceptible for illusions is a good sign. It shows that they're making effective use of the data they're given. On the other hand, if the shortcuts the model takes are unexpected or unintended by the programmer, we should correct for them and add human priors to the models. But we can always remember that every illusion that we find is a great window to the inner workings of the system, so it's a great feature.